So we need to find the pH of a solution, of an acid solution. So what we're going to do is we're going to start by writing a dissociation reaction for this particular acid. So acetic acid is that. We're going to put it in water, which is liquid. And acetic is not on our list of strong acids, so it's a weak acid, so we're going to use a double arrow here. And it's going to produce the conjugate base here of acetate ion in solution, aqueous. And of course, as with any acid, it's going to make hydronium ion. So there's our reaction. So because it's weak, we cannot say that it all dissociates. So we're going to need to make an ice chart. And the initial acid concentration is given in the problem. It's 0.200. Before dissociation, we have none of these things. The change, we're going to use up x here, all coefficients of 1. So we're going to make x here, and we're going to make x here. So at equilibrium, we're going to have 0.200 minus x, and x. So our K expression, our Ka for this reaction is going to be our conjugate base times our conjugate acid, all over the original acid concentration. Not original, but equilibrium of original acid. And so we can now go ahead and plug those in. We're going to have, this is going to be x times x over 0.2 minus x. And that's all going to be equal to K. So we're going to need a K value for acetic acid. So we're going to get into our appendix in our book. And we can see that acetic acid is the very first one listed here. It's got a K value of 1.8 times 10 to the negative fifth. So we'll write that out. And now we're going to make the small x approximation assumption. And so we'll forget about the minus x there. And so we're left with, we're going to multiply both sides by 0.2. And so that's going to give us 0.200 times 1.8 times 10 to the negative fifth is going to be 3.6 times 10 to the negative sixth. But that equals x squared, so we're going to now take the square root of that answer. And we get an x value of 1.9 times 10 to the negative third, which is 0.0019 molar. Now the